This has been a rather mathematical discussion, and it's going to continue to be. But I just want to recap a few of the things you should take away. Now that we know that K is related to delta G, it's got to also be related to delta H and delta S, because we know that delta G is related to delta H and delta S. As long as we stay in the same phase, delta H and delta S don't change very much with changes in temperature. And that allows us to play a few games as far as the equations that we have come up with. Interestingly, the influence of delta H on K decreases as temperature increases. If you think about it, delta G is delta H minus T delta S. The bigger T is, the more delta S gets involved. Increasing a temperature will shift a reaction towards the side that's opposite the energy term. So if exothermic, so that heat and energy is being released. If you increase temperature, that's like shoving energy back at it, and it's going to shift it to the opposite side. So the opposite side of the energy term. And because of that, increasing temperature will promote an endothermic reaction and inhibit an exothermic reaction. Here is another reaction. Carbon dioxide can be broken up into carbon monoxide and oxygen. This sounds like a bad plan to me since this stuff's poisonous, but okay, you can do it. If you plot the logarithm of K on the y-axis and 1 over the temperature on the x-axis, you're going to get a straight line. I know that K equals E to the negative delta G over RT, which means that it is also equal to E to the minus delta H plus T delta S over RT, which means I can break it up into E to the minus delta H over RT plus delta S over R, because the T's cancel, right? If I take the logarithm of both sides, I have the natural log of K. Ooh, natural log of K, that's what I decided I was going to use for Y, right? Equals, if I'm taking the natural log of this, I'm just going to take the exponent. So that's going to be minus delta H. And I'm going to break it up as over R and then 1 over T. And then also delta S over R. What this shows is that this looks like Y. I said this was going to be on the Y-axis. Equals, this is M, and 1 over T is X. There it is, 1 over T is the X-axis, plus this is your B. So this is the slope-intercept form of a line. So it turns out that the plot of the logarithm of K, when plotted against 1 over T, ends up being a straight line. If you have a positive slope, it was exothermic. If you have a negative slope, it's endothermic, because this had a minus here, right? When delta H is negative, that's exothermic. If delta H is negative, then this other negative is going to cancel, and you would end up with a positive slope. So exothermic will give you the positive slope. And of course, negative slope is endothermic. Once I've pointed out the fact that this is the slope-intercept form of an equation, you can go back to either the Clausius-Clapeyron equation or the Van't Hoff equation and realize that that equation is also the equation of a line, as long as you're talking about logarithms and 1 over T, but it's in a different form. You know, there are different forms of lines. You can write a line in the general form, right? Which is not really very useful unless you're programming computers, but you can do it. You can also use the point slope form, and that is what you find is the Van't Hoff equation, but it's also would also show you a line. We know that if delta G of the reaction is less than 0, the reaction is going to be spontaneous and move in the forward direction, which will create more products, and the reactants are going to go down. The more negative delta G is, the more products you're going to create before you get to equilibrium. And if you are thinking about a positive delta G, it can be interpreted as meaning more than just that the reaction is non-spontaneous. because we have a way of converting that into what K is. And we will find out that, in fact, a few products might be created before the equilibrium is reached. It is possible for that to happen, just not very many.